Good morning, everyone.
Morning.
Good. All right, so this is our very last class for the physics course. And today we just want to quickly look at some important things that we have to cover because they're necessary. We are not covering the whole of chapter 13. So we're just taking the first two parts. We dealt with one part on Monday. We want to look at the last part now. And we're starting with fluid in motion. So far, we've been looking at static fluids. I've been looking at fluids that are stationary, but now we want to advance a little bit to touching fluid in motion. Now, the concept of fluid in motion, or understanding the concept of fluid in motion, is very complex. Okay, the whole theory of fluid dynamics dealt with that. But what we're going to look at today is just like a brief introduction, so that when you get to advance in the study of fluid, especially how it applies to the circulatory system, for those of you in the medical sciences or biological sciences, and those that want to advance in physical sciences, studying fluid dynamics. Some of these concepts will not be totally new to you. So that's the essence of looking at this basic concept. Okay. So peeping a little bit into fluids in motion, we want to make some assumptions that will help us avoid the complexity and complications that has to do with the dynamics of fluid in motion. Okay, we were able to look extensively into the static fluid, but we'll be applying some of those principles from the static fluid idea to explaining fluid in motion. So want to look at the basic assumption. There are acceptable assumptions that are generally used at the fundamental stage to avoid complexity in the discussion of fluid in motion. So one of which is that fluids are incompressible. Okay. Now, when we say fluid, you know, we're talking about the flowing objects or flowing liquids. And by that, we are referring to not just liquid, but also the gas and liquid makes up fluid. Okay, so, and that is why we are emphasizing here that this assumption, saying that first assumption would be that fluids are incompressible. It's a very good assumption for liquid, and it also holds true for a moving gas, okay, such as air, which is the most common one that we interact with on a daily basis. So the example or instance for which air can display the assumption that it is incompressible is if you have like amount of air moving at 100 miles per hour slammed on the wall, the density will not really change, but with a minute value of 1%. Simply means that such fluid volume cannot be compressed. Okay, so the second assumption is that we're going to stay within the domain of the flow, assumption that the flow is steady. Fluid flow is not always steady, but we'll have moments when they are steady. So it means that we're just going to stay within the domain of the steady fluid flow. Okay, so we're assuming it's incompressible, and we're assuming that fluid flow is steady. And what do we mean by that? When we have a flowing liquid, the fluid velocity at the point in the liquid is constant. And that is what we mean by flow is steady. So it does not fluctuate nor change with time. It remains the same. For any fluid that is flowing or whose flow is constant or is moving at a constant velocity, that is, it's not fluctuating or changing over time, we call such flow, take note of this word, okay? We call it laminar flow. Now, we have a counterflow such that the velocity is going to change and the flow becomes complex. To describe such flow, we use the word turbulence flow. And we know turbulence kind of spell negativity, but it's actually a kind of description for flow whose velocity is changing or fluctuating at a constant rate. Fluctuating like randomly. Let me not use the word constant rate. Okay. So we have the image before us here. We use this image to describe clearly the difference between the turbulence and the laminar flow. You see, when you look at the region for laminar flow, you see that it has smooth contours. You can actually define the lines. You can see the clear definition of the lines. But when you get to the turbulence region, they are so mixed, moving randomly, such that the contours are not well defined. Okay, so when we say the second assumption is to stay within the domain of laminar flow, it means we are just going to stay within the domain where the flow lines are clearly seen and they are defined with smooth contours that can be described. Okay, so this is majorly the difference between the turbulence and the laminar flow, and it is the laminar flow that we use as our model for the description of fluid throughout the discourse of fluid in motion. Okay, so whenever we talk about the subject fluid, we always have to look at one of the characteristics that describe fluid in motion, one of which is viscosity with a symbol nu. Now, we have looked at viscosity in chapter 5 when we're looking at applying Newton's law. Okay, when we're looking at applying Newton's law, and we looked at viscosity and we discussed it with reference to drag. I think that was like a class after our drag lab. We emphasized there that viscosity is similar to friction, and it simply means resistance to flow, just like friction is the resistance to motion. Okay, so viscosity should be viewed as the counter force like friction in liquid. It means that if you understand the idea of friction very well, it will help in understanding how we're applying viscosity to fluid motion. Okay, so, and when we discussed in chapter 5, we use Reynolds number to describe the relationship or the ratio of the inertial forces of viscous to the ratio of the initial forces to viscous forces in an object moving in fluid. So we said that we use Reynolds number to actually define when the viscosity of an object is high or low and when it can be ignored. So we also want to use the idea of what we learned about Reynolds number to apply to the concept of the fluid in motion. And what is the basic idea we want to take from there? We want to emphasize that For fluid in motion, when you determine the Reynolds number, which is the ratio of the inertial forces to the viscous force, when it is large, the viscous forces are small. And what is the importance of that? It can be ignored. Just like we can also, in certain scenarios, ignore friction and drag forces in our calculation, so also we can ignore the forces, the viscous force, or ignore viscosity in some of our application. And we do that mostly when we have a large flow, like the flow of the ocean or river. You have to do some calculation in respect to the bridge construction and all that. You factor the flow, and sometimes you have to ignore viscosity because the flow is large. All right, so those are scenarios when we ignore viscosity. Okay, so let's see an example of when viscosity is ignored and when it is not. We said Reynolds number helps us define that. When it's large, the viscous forces are small and can be ignored. So let's say an example here. The water flow at, this is the speed of the flow, 1 meter per second in a river that is 2 meters deep. The Reynolds number, you can be asked to determine the Reynolds number and tell if the Reynolds number should not be ignored and factored into decision making or not. Okay, so we take the formula of Reynolds number. It did not change. It's the same formula we have seen from chapter 5. Reynolds number representing the RE. Then we'll have the density of the fluid, the speed or velocity of the fluid, the depth, and the viscosity. So because we have seen this, that's why I didn't have to define out the parameters. So you can always refer to the discussion of viscosity in chapter 5. We're just building on it using the idea to explain fluid in motion. Okay, so we know that for water, the density is 1,000 kilogram per meter cube, the speed and the depth as given. Then we'll have the viscosity also as 1 times 1,000 raised to power minus 5, which is a constant and it will be supplied. For the viscosity of water, I think we put a table like that also in chapter 5. So inputting that into our formula, we got the Reynolds number to be 20 million. And you remember that in chapter 5, we described that when a Reynolds number is, I think it's 100,000 and above, then we can refer to it as large. And we had the large, the middle, and the small Reynolds number values. Okay, and we just picked the large and the small. We really did not discuss the middle because the middle applies to the complexity actually of fluid dynamics. Okay, and we'll not get far into that. So we have 2,000, but let's look at another scenario where you have the blood flow moving in the arteries with a diameter of 0.0002 meters and the speed of 0.003 meter per second. If we determine the Reynolds number, we see that it is small, and this implies that here we can ignore the viscous force because it's small, but here we cannot. So whenever they are doing calculation about how they will be sending fluids or blood flow, regulating the heart beats to control the flow of blood in the veins and arteries, they factor the Reynolds number because it will influence greatly the decision to that design. Now, apart from the properties such as Reynolds number and viscosity, we have other properties or other subject that applies to the description of fluid in motion that are very important to understanding how fluid flow, especially when they are changing from a large area or surface volume to a smaller size. And we'll be looking at 3 equations, which is about the concluding this part of our discussion. 3 equations outside the Reynolds number and viscosity ideas. Okay, so the first is the equation of continuity. The second will be the Bernoulli's equation, and the third will be the Fouasse equation, which is the last one. So let's start with the equation of continuity. The equation of continuity actually says, because we said we're factoring, remember our assumption throughout is what we'll be using. Equation of continuity says that volume of an incompressible fluid entering one part of a tube or pipe must match or is equal to the volume leaving the downstream. Okay, so let's see the figure before us. We'll see the figure before us is a description of the flow speed change in a tampered tube. Okay, now we have examples of tampered tube every day. You use your toothbrush, you press the fluid from inside the toothpaste on your brush. That is a typical example of a tampered tube. So you see that the content inside is pushed through the other side to get the small or whatever fluid or liquid that is inside that tube. Okay, we have other examples such as the flow of blood in our arteries, moving from the heart that will adjust to different sizes of the tube of our arteries. Also, we'll have the flow of oil in pipes and so on. So we meet tampered tube every day to control the transportation of fluid in several systems. So if we look critically at this to understand the statement of the equation of continuity, which says the volume entering is equal to the volume leaving. So it establishes that change in volume for 1, let's use the big size as V1, is equal to change in volume of B2. That is the basic expression or statement of equation of continuity. So when you press the fluid here, it moves a distance that I want to describe as change in x1. And when you do that, you see it will force through the smaller part of the tube a distance as well, which is change in S2. And the area for the A1, area for the A2, we have established that this is the statement V1, volume of 1 will be equal to the volume, change in volume of 2. So when you press the little, you see how widely spread it is, such that the volume for change in V2 is the area and the distance, you know, volume is L cubed. So area is L squared plus this one, L1, giving you L cubed. Okay. So that's how we got to express volume as area times the distance. So the volume, if the volume is area times the distance, and we know that from V, remember what we're looking at is what? Speed, all right? Distance, change in distance with time. When you press the fluid here, how much time are you spending to press it to get out what you want? When you press, you press at a certain speed and it's going to come out at a certain speed. Okay, so V equal to this V you are seeing here is different from this one. Okay, this is volume, this is velocity. All right, so change in X is therefore V, velocity, change in time. If you substitute this into this equation, put it in here, we will have an expression that gives us the change in volume equal to the area. Substitute your velocity, change in time, which is this. So we have change in volume equal to area velocity of 1 over times change in time. All right. So if this is true, it means that we will have also change in V2 being equal to A2 V2 change in time, right? So if we equate, put that into this equation, we will have V1 being A1 V1 change in T being equal to A2 V2, this V is velocity, not volume, okay? Change in T. So T takes care of T. We will now have product of area and volume for 1 being equal to area and volume for 2, which is this. So it is this equation that we call the equation of continuity, which relates the velocity, which is the speed, which relates the speed of the incompressible fluid to the cross-sectional area of the fluid that it is passing through. Okay, so that is simply what the continuity theory is describing. And what is the consequence of this continuity theory? It's telling us that the flow is faster at the narrow part than the wider part. If you look at the velocity vector diagram, the arrow here is longer than this one. So you see the flow is faster on this narrow part than the larger part. That is one. We have other consequences, which the understanding of which we use to describe the volume flow rate Q. So if you look at the diagram we have here, you see the area here is larger than this one. What does that tell you? It means that the speed here is higher than this one. We said the flow at the narrower part is faster than that of the wider part. So it is this idea that we also use in the design of your water tap openings and the pipes that will run in the house. Okay, so simply put, the speed of water is inversely proportional to the diameter of the stream. Okay, so the speed is inversely proportional to the diameter of the stream. If you look at this diagram, you see that as it's coming out, the area here is wider, the flow, the speed here is larger than the one here. Okay, so distance also plays an important role, which we'll be seeing again. So let's quickly look at an example. The question says a garden hose has an inside diameter of 16 mm and the hose can fill 10-liter bucket in 20 seconds. The question is, what is the speed of the water out of the end of the hose? And what will you do to increase the speed 4 times, to make it 4 times greater? So we apply our equation here. Take note of this, the flow rate change in volume being equal to V over A for a steady flow, okay? That is for laminar flow. So applying that, if Q equal to VA, V therefore, which is the speed, will be equal to what you have here, QA. And We determine our Q from the equation change in volume over change in time. They give us the volume and they give us the time. We obtain this in liter per second. So before we can apply it into equation, we have to change the unit to standard value to obtain 5 times 10 raised to the power minus 4 meter cube per second. So that's what we put here. The radius, area is pi radius square. The radius, the diameter was given as 16 mm, convert to meters, divide by 2. That is how we got this value. And we got our final speed to be 2.5 meter per second. So what do we do in the second part? They said, what can be done to increase the speed by a factor of 4, make it 4 times greater? So to make that 4 times greater, we see in this relationship that we have to work on the area. Remember our first diagram, this one, telling us that we increase the area, we reduce the speed, we reduce the area, we increase the speed. Okay, it means that the area has to reduce by a factor of 4. Okay, so if the diameter is given as 18 and we got our radius, which is divided by 2, we have to do by 4 to get that factor. Therefore, the diameter will have to be 8 millimeter per second. That is reducing the area by a factor of 4. Okay, so let's look at in the description of a continuity equation, we have other parameters that helps us understand fluid as well. One of which is when representing fluid, we use the term streamline and fluid elements. Okay, so streamline are simply parts taken by the particle of fluid. Okay, if you can point out a particle of fluid, especially in laminar flow, you see them clearly with defined contours. The particles of fluid has a trajectory. That trajectory is what we call the streamlines. Okay, and we'll have another one, which is the fluid element will be seen in the next slide. It's simply talking about the movement of a certain or volume or large amount of fluid. We call such fluid element. And when we are focusing on the particle, it is called streamline. So you have multiple streamlines inside a pack called fluid element. So now we have said this is the trajectory followed by the particle. So we have, this is a trajectory, this is a trajectory, this is a trajectory. The streamline, one of the characteristics is that they never crosses each other. Okay, they never cross. Then we'll also have that the particle velocity is a tangent to the streamline as described here, tangent to the curve of that streamline. We'll also have, that means if you have a defined streamline, a straight one, it implies constant velocity. Okay, so you don't have to, the tangent will just fit into that line. So the speed is higher when the streamlines are closer. So when they are wide apart, it simply implies that the flow is slow. When they are closer, packed together, it is fast. So you see the wind, which is the fluid, the gas over the car, you see how it took the contour and the trajectory of each of the particles can be seen. See, when they are closer together, when they are far apart, tells you the speed increases when they are tight, slows down when they are wide apart. Okay, so we mentioned, I explained earlier what the fluid element is. You can see the streamline. These are streamline, but this one is the fluid element. Now, one distinct thing about fluid element is that it has a defined shape. In streamlines, you're defining line. You're not using shape to define that. But when you talk about fluid element, which is the compound of streamlines, you talk about a defined shape. You see here, they are close together. Here, they are spread out. What does that tell you? High speed, low speed, right? And then the same volume taking different shape at certain speed. So the fluid element is that shape. You see, as it's going, it's getting wider, it's taking another shape. The volume of fluid together is what we call fluid elements. All right. So we use those two basic terminology to define and understand the flow of motion. So let's quickly look a little bit on fluid dynamics. Now, the equation of continuity described to us the motion of objects, but did not specify why fluids are actually moving, what is actually inducing the motion. Okay, so when we want to talk about fluid dynamics, we actually want to look at what is inducing that motion, what are the laws governing that motion. And it is this dynamics that will help us look at the two other equations that we said we'll be looking at today. So we see a fluid here, a description of a tampered tube. You notice if you look at the R vector diagram of the speed or velocity, it is increasing as it goes into the smaller size of the tube. Okay, so we want to use the Newton's second law also because it applies here to understand how that this fluid is accelerating. Okay, we can notice that there is no external force. We notice that there is no force of gravity since it's moving horizontally. So where is this force actually coming from? The force is actually coming from the fluid. Remember fluid elements, the bulk of fluid, volume of fluid together, pushing at the end of each other with the walls of the container and also pushing at the fluid particles. So it has a surrounding force that we'll call the pressure force. Okay, so it means that we're going to be applying our understanding of the Newton's second law and pressure to describing fluid flow. So, and that says that the net force on a fluid element due to the pressure point from a low goes from a high to low pressure. This diagram specifically shows that, look at the net force is always going to be in the direction of what? The acceleration, remember Newton's second law. So we'll see the force here from the left is higher than that of the right. So the net force is moving in that direction. That's acceleration is towards that direction. And the relationship of the pressure to the area and force is what we describe with the word Bernoulli's effect. Okay, and it simply tells us that the pressure is higher at the point along the streamline where the fluid is moving slower. So the pressure in the larger area of that tampered tube is higher than that of the smaller parts. Okay, so with high pressure, the speed is low, but with smaller pressure, the speed is high. So we look at that with the relationship that, remember your pressure equation is P equal to FA, right? That means force is equal to PA. That is what you have here. So if force is equal to PA, and we can see a kind of pressure difference, which emphasizes a flow cannot happen if there's no pressure difference, okay? So we have the force on the left going to the positive direction, the force on the right going to the negative direction. So we'll have FL minus FR, which if you substitute this equation, you will have FL, P, F is equal to P on the left A, and P on the right A. So if you bring out A, that's how we'll have this expression. And this actually implies change in pressure. So we'll have F net being equal to area times change in pressure. Okay, and that statement simply tells you that the pressure in the larger part is higher than that in the smaller part, and that is why it moves at that slow rate. Okay, so we'll have the instrument that we use to measure the fluid speed, and that instrument is designed according to the venturi tube. We have several devices with different names, but they use the principle of the venturi tube. Okay, so the device, the venturi tube, is what we use to measure the speed of fluid. And how does it do that? By factoring the difference in pressure and also the difference in the distance of this. So let's assume you have a tampered tube. We put an opening. Because the fluid flow here is slow, the fluid will flow and fill up these opening tubes. All right, it goes high. And the fluid flow here is faster. It cannot really fill up to the length like it did when it was slow. So the faster pressure here, the faster motion here at lower pressure made this to be not to be filled up as high as the one on this side. So we'll apply the equation we have seen before from the static pressure equation, that the pressure at the point 1 will be what is our PO, atmospheric pressure acting here, being equal to the density, the gravity, and the distance here from the midstream line of that tube. Okay. But at the point 3, that apply also to point 2. At point 3, where the fluid translates to a smaller portion, we have the change in pressure to be actually the change in this distance, which is change in D1 and D3. You see the D3? Let me remove all this so you see it clearly. The distance from the midline to the fill in that tube. So this is how the flow rate across this bend can be determined using this venturi tube. Okay. So this simple design is what is put together in many devices that we use to measure the flow speed of liquid. So let's see how we have emphasized that this is actually the application we call the Bernoulli effect. Let's see how that plays out in real life. We have different instances where we apply the Bernoulli's effect to science and technology. And basically, before we mention other examples, let's see how it works. I said that when you have even spacing, it means what? The constant velocity for streamline description. So we have a description of the wind speeding up across the crest of a hill. This is the hill here. The winds here, they are moving at constant speed. You see the speed here is constant, but once they are cresting or moving over a budge, you see something happens to the velocity vector. It increases. That simply tells you that the higher air speed here has lower pressure. So at lower pressure, remember your tiny tube, tampered tube, low pressure, faster speed, large pressure, lower speed, right? So as these trajectories of the particle of wind crest or move over an hill, they speed up. And it is that principle that is applied. If you look at that bed in the very first description of our introduction for fluid, you see the bed building up momentum before it goes airbound. It's building up, spread out its wing, trying to maximize these principles that that nature has taught us from looking at those beds, to go into a lift, to go into the air. And the same applies also to the design of plane, because we know that the fluid that will move, this is example, the wing of a plane, once it's advancing, it's in motion in that fluid, the fluid over the wings will have high speed. The one under will be moving slower and causes a push that bring about the force called lift. Okay, so it will lift the plane. As you control with a certain design in the plane, you get a lift to the desired height that you want. So they are maximizing the adjustment of the low pressure, high pressure to define the speed and bringing about the lift force in that, on that plane design. Okay, so a lot of calculations are put in place for just giving you the ideas or points to how do I appreciate the understanding of these principles in real life. Okay, so we look at the second equation, which is the Bernoulli equation. The Bernoulli equation simply describes the fluid change when there's an elevation in, let's say, the fluid flow. It actually brings or factor in the force of gravity, that it can actually cause an increase or a speed up or a decrease in the fluid speed. Okay, these are meerkats. When they burrow holes, they apply this principle in their senses to determine what is happening outside. You know, the flow of fluid through their holes help them have a sense of what is happening outside their holes. So apart from the application of biological animals senses in this, we have a better way to applying this Bernoulli's equation in the construction and design of tubes. Okay, so it is actually the understanding of fluid dynamics that we use to design the weight pipes that are used to transport large fluids, the gases, or to different parts of the world. Okay, so remember when we treated this in chapter 5, we wrote out this equation. Sorry. Okay, where this kinetic energy, changing kinetic energy plus changing potential energy equals to work. That is simply the principle that Bernoulli applied and factored the parameters using the changes in the flow, which are the principles we looked at to derive what we call Bernoulli's equation. Don't be scared of all this. They are not mystical. They are everything you've seen before. So this, when we say potential here, we're referring to the gravitational potential. You remember gravitational potential, the force on every object above the ground. All right. So the gravitational potential plus change in kinetic energy equals to work done. How did Bernoulli apply this? Bernoulli brought, if this is true, and we'll have different surface area of tube, a tampered tube typically. That means if we can establish a relationship between these two sides, we can apply this principle to describe actually the work done when there's a flow in this kind of tube. So kinetic energy is, because there are two sides, that's what brought about those changes that will apply. Half mv squared, right? If k equal to half mv squared as we know it, you remember that from the relationship density equal to what? Mass over volume. Mass, therefore, will be equal to density V, right? So if you substitute that into this, that's how we'll have mass being the product of density and volume, then the velocity squared. So the equation is what you know. You see that it's not strange. So this is actually half mv squared expressed in relation to fluid because of the word density. So for the part one, that is the kinetic energy for this side, and this is kinetic energy for the second side. So it means that changing kinetic energy, which will be the K2 minus K1, substitute this expression into it, you have K2 minus K1 expressed as this part. Now, same applies to the potential. Potential energies have mgh, h being the height, which we can use the description y to represent here. You know, this is your m, right? Product of mass and volume. Then gh, this is depth or height. Okay, so change in potential is also this. So we have done for K, we have done for U. We want to use the understanding of work done as well before we put the equation together into this. That is what all this is about. So work done equals to force times distance. And we know that force from P equal to FA, force equal to PA. That's how we got this one, times distance. So work done as force as distance equal to this for A part. That's for the part point one here. And then for part B here. Therefore, the net work done in a system W will be the sum of this plus this, because we have the negative here, negative work done. The force here is going this way, positive, and the force here is going this way, negative. So that's where the negative came from. This is the positive work done, and this is negative work done. Positive work done by F1, negative work done by F2 because of their direction. Okay, so we have this. So we'll put this, and this into this equation. If we do that, we'll have the full expression here. And you notice this is constant, so it can actually go off. You strike out the V. If we cancel all the V's, change in V's, and rearrange, we'll have what we call the Bernoulli equation, which is given as this. You do that, you collect like terms. What I mean by like terms is collect all the one for the point 2 and the one for the point 1. Equating both gives you the Bernoulli's equation. You see, it's a straightforward one. For those of you who love mathematics, you enjoy proving the Bernoulli's equation. So we'll look at this word is a French word, so pardon me if I don't pronounce it correctly. The Poisson equation, Poisson equation, yes. So viscosity and Poisson's equation. What did Bernoulli applied actually this basic principle of the work done? What did Poisson really do? He used this equation to help us understand the relationship between the radius and the lead factor in fluid flow. All of which also goes back to this venturi tube, which is the understanding of how fluid flow can be measured. Okay, so let's just quickly go straight to what the Poisson equation talk about. It established the pressure difference needed to keep the fluid flowing. And it stated that the pressure difference is actually proportional to the viscosity. That is what Poisson equation gave to us. And it brought in the concept of the tube flow again, described the surface area A, that the pressure difference, which we already know that a fluid in motion will always be as a result of pressure difference between point A and point B. Okay, so if we give the relationship as change, that's the pressure difference being equal to the derivation of all this is what we didn't bother to put because it's very lengthy. And since you are not going to be applying so much, we just have to point it out here. So if the expression of the pressure difference is given as 8 pi nu, which is the viscosity, which shows you the direct proportionality relationship, and all this being the constant of proportionality with respect to the length of this tube and the average speed over the area. And area is given as pi radius squared. If you substitute that into this equation, you will have, and make V the subject of formula, V average, you have the expression here. So the Poisson equation also factored that in a tube, for an ideal tube, you have all the velocity, the streamlines flowing at the same rate, but actually in reality, for a viscous fluid, once the viscosity comes into play, the one at the middle, the maximum velocity is felt at the center of the tube. And that is why we describe even in venturi tube using the mid streamline as our relationship. The same apply for the rate, and applying the rate, understanding of our rate as V over change in T, and our area as AR squared, given the derived average equation for V, we now have that substituting this into V, that the rate Q is given as, remember our first equation, V equal to A, right, at the beginning. If the rate is given as this, and the expression of Q itself is actually changed in volume, we will now apply these two, understanding this and this, to arrive at the Poisson equation for viscous flow through tube and radius. And how did he do that? Let's quickly, oh, time has gone. Okay, A equal to V, puts this as A, right? And V average is given as this. So bring in A as this, bring in V as this, we'll have this equation because they will cancel out. Pi came to the top from the area, R, multiplying R to give you this R squared. Once you write it out, you arrive at this final one. Okay, thank you. We have come to the end, the very end of our discussion. So we'll be meeting again on Tuesday, right? And depending when we meet again in exam, we'll always have to, okay, why is the pressure higher when the surface area is greater?
Yeah, that was about the earlier bit with in an area of smaller diameter, the pressure experienced by the water is less.
Okay, so
what are we defining pressure as? Because I'm just a little bit confused there.
Pressure is defined from our basic definition of pressure, P equal to F over A. Pressure is equal to force over area. So
right,
pressure actually has inverse proportionality relationship to area. You get it? So when P,
as area increased, pressure decreases?
Yes.
Yep.
So this is actually what is happening there. When you reduce A, P goes up, okay?
Okay, so this is the pressure being exerted on the water by the container?
I didn't get that.
Is this the pressure being exerted on the water by the container?
Yes, the pressure exerted on the water, the force actually is from the pressure within the molecules of those water, because there's no external force. The force is actually coming from the force from the container as the molecules of water collide with the container and the fluid element, which forms the fluid element. Remember, the very idea is the streamline, one particle of fluid. When they are compact together and they press against the wall of the container, the pressure comes in from the fluid element and tend to push. So if there is a pressure difference, like there's a shape where it can actually go from the higher pressure to the lower one, it tends to flow to that direction.
Okay.
So that pressure difference is what now induces the flow, like calling it just like the pull of gravity on object above the ground. So that's smaller, the difference pulls from the region of high to low.
Okay, how does this relate to a laminar flow then, or are we just working with it, assuming it's laminar?
The definition of laminar flow?
Yeah, because are we assuming it's like this or disorganized? I'm just trying to understand if it's like a turbulent system or not.
Okay, let me be sure I understand your question. You want to know what exactly is laminar flow? Okay.
Well, it would seem to me as increase because the walls are closer to you and therefore there's less spaces you can go to. And here we're saying the pressure decreases in a smaller diameter tube. I'm just trying to understand what is happening. Because if we're assuming that water molecules are just kind of moving around, if the diameter is less, they're more likely to come in contact with a wall. So that would make me to think then the overall force experienced on the walls is greater.
Okay, so here.
Does that make sense?
Yeah, the argument makes sense, but in principle,
like I get it, but I'm just not quite. I just want to understand it properly. So,
okay, when you look at the relationship, I'm not sure if I'm getting you correctly, but if I'm not, just correct me, okay? When you look at this tempered fluid, I think this is the description where you want the clarity, right? The fluid.
I think so, yeah.
Okay. So the basic thing when you, let's take that example of your toothpaste, when you press, the
so that's the external force.
Yes, a volume that will move from here. When we looked at the description of laminar and fluid elements, when when it was small, as it's getting wider, the fluid element shape got bigger, right? So the inverse is like what is happening here. The shape here and the shape here, the V will be equal, because what you press here is actually what will come out here. The difference, yes.
So
what you
volume
press
constant
here, yes. So is what will come out here. But what is actually going to happen to that element or fluid element is that the shape will adjust according to the area available.
Okay, so if we're looking at this
yes,
cross-sectional area.
Yes.
Okay.
So it is that proportionality that defines, also putting into consideration the relationship of the force applied, the area, which is pressure being equal to FA, the force being pressure and A. All defined
I get
by
it. That makes sense if we're defining it relative to volume. So does that mean if we define it relative to the it's delta X here, so if that were to be the same, would that mean that the pressure would be less?
The delta S, yes.
The volume is different? While volume is constant, pressure decreases. That makes sense.
When volume is constant.
Yeah, right?
The pressure decreases. Okay, it will not put it that way, in the sense that if if there's no pressure difference, there will not be flow. It will be, we will now describe it with the principle of the static pressure. Yes.
Okay.
Which we have seen in the last class using the description of atmospheric pressure difference, yes, for static fluid. Yep. But when it comes to fluid in motion, we use this principle of volume, which also tells you that the distance that this fluid will move is actually going to be in the same ratio, the distance here. And that is why when we express this equation, we brought in the distance, defining it from velocity, because it's that push you give, the speed, change in x, over the time spent to do that push, changing t.
Okay.
Okay, so we now have here, when we equated the volume, factoring the time, later the time canceled out, because it's the same time as you push that you receive the result.
Okay, so in a container full of water,
yeah,
it's going to experience that. If the container wasn't full of water, the forces would be different then?
Yes.
Like if it was half full? Okay, okay, I think I get it now. Thank you.
You're welcome. So do we have any other question? For those mathematics lovers.
I have a question. Should we come to pick up our stuff? Can we come now after class is done, or are you not in the school as yet?
You'll just give me 30 minutes to go from where I am to the school.
Okay, okay, sounds good.
Okay,
thank you.
All right. And if after 4 o'clock, if you can come within the time and you want to come after 4 o'clock, I'm going to paste it on the wall outside the lab. So you just pick up yours. At the end of Friday, I'll come and take whatever is remaining in that envelope outside. But that means you'll be leaving your script for every other person to view. Okay. So you come, just give me 30 minutes and I'll be in school. Okay.
Okay,
thank you. Thank you. Yeah, I'm still available to email, Zoom, phone call till exam is over. Okay. Thank you. See you. I got your mail, sure, I'll reply you. Okay.
Okay, thank you.
You're welcome. All right. Have a great day. See some of you later. Bye.